is from team B31, automating quantification of intracranial aneurysms. Go ahead.
Okay, hi, everyone. We are team B31, as Dr. Goldberg just said. And on this call on our team, we have Ali Adali, Jenna Grishep, Anna Kratsky, Michaela Young, and myself, Grayson Knight. And our project is automating quantification of intracranial aneurysms. So a little background, an intracranial aneurysm is a bulging or a dilation of a weakened arterial wall in the head, and risk factors of having an aneurysm include older age, hypertension, smoking, and there's many more, but these are the top 3 that are typically used. About 2% of the population have an unruptured aneurysm, with a rupture occurring about every 18 minutes in the US alone. Determining the size and shape of the aneurysm is critical for evaluating the severity of the aneurysm with the possibility of rupture. Retaining the images for future comparison is also important for determining the progression of the aneurysm. For patients entering a hospital with the complaint of a headache, about 1 to 4% of patients had a ruptured intracranial aneurysm, which may not seem like much, but the most common complaint of patients entering a hospital is a headache. Imaging for intracranial aneurysms include MR imaging, CTA, and IADSA. Treatment for the intracranial aneurysm includes surgery if the aneurysm has a high risk of rupture. Otherwise, continued image monitoring for the aneurysm is required for treatment.
So as Grayson mentioned, it is crucial for radiologists to determine the size of the intracranial aneurysm to see the severity of a patient's aneurysm and to determine their treatment plan. The current methods that are being used by radiologists is all manual quantification through the use of the computer caliper tool. So this introduces human error as well as it's not consistent or consistently reproducible. Lastly, it is also time consuming for each of them to go and use a computer tool each time that they want to measure the aneurysm. So our problem objective statement targets those problems, and our problem objective statement is to develop an approach to quantify brain aneurysms by automating the current process as well as minimizing that human error. So our top 3 customer needs for the project are shown here, as well as the target specs that go along with them. Our first customer need includes the user interface needing to output the images and metrics of the intracranial aneurysms. The 2 target specs that go along with that are displaying those images of the aneurysm, blood vessel, and the brain slice, as well as displaying the vessel to size ratio. The next customer need includes the algorithm needing to measure the size of the aneurysm, with the target spec of the user interface displaying the max diameter of the blood vessel and aneurysm to the screen. Our last customer need includes the algorithm measurements needing to be accurate, which goes along with the 2 target specs of the error of the algorithm diameter measurements needing to be minimal, and the percent error of the percent change of the aneurysm diameters of a simulation to be minimal as well. The ideal values for those target specs are listed in the right-hand column, with the first 3 being just yes or no if they display or if they do not. So the ideal value for those 3 are yes, and the last 2, the error of the algorithm diameter measurements, the ideal value is to be less than or equal to the plus or minus 1.2 millimeters, and the percent error of the percent change to be minimal.
In order to meet the target specs and fulfill the customer needs explained previously by Ali, we have created a novel software program that is able to obtain metrics about an input intracranial aneurysm. The flowchart on this slide is an outline of the image processing and calculations necessary to obtain proper metrics. In the next few slides, we'll be diving deeper into each box. The first section of our program is all about inputting the image and isolating the intracranial aneurysm. The data we input into our program consists of 2 nifty files. One of these files contains MRI data of a human brain containing an aneurysm. This is seen on the right-hand side of the screen. The other file, on the left-hand side of your screen, contains the very small intracranial aneurysm mask, which highlights where in the brain the intracranial aneurysm is located. Using these images, we are able to isolate the slides where the aneurysm occurs. In the case of the images on the screen, this is about 9 total slices. Then, we determine the pixel location in each slice where the aneurysm is.
The next section is to use thresholding image processing techniques as well as information about where the aneurysm is to find the blood vessel that it's located next to. So in order to threshold, after we track the aneurysm on the brain image, we use the smallest pixel value that's comprising the aneurysm in order to threshold the brain image. And then once we have a thresholded image, the next step is to find the blood vessel that the aneurysm is attached to. So the way that we went about doing this is we used an image processing technique called connected components. So MATLAB will apply the BW label function to the previously thresholded image, and then MATLAB will use the location information from the previous section to find which connected component is closest to the location of the aneurysm. The connected components are then labeled with their own unique identifier that corresponds to a grayscale value from the smallest numerical identifier. So the image on the left is basically the image on the right, just in color so that you can see each of the connected components. Once the code finds the correct component that the aneurysm is attached to, it then segments it out as seen as on the right image, which consists of the blood vessel and the aneurysm. So then to visualize the image on the left, directly to the left of that is the blood vessel highlighted in pink with the aneurysm in white. And then those two overlaid images get overlaid again on top of the original brain image. And then that's in the top left corner, and the bottom left corner shows a zoomed in version of the region of interest. So then once we have the mask of the blood vessel and the aneurysm, we will be able to use various MATLAB functions to help us obtain the metrics that we desire. So we use a function called region props, and region props allows us to analyze a binary image, all the white spaces in a binary image, basically. And what we used from region props is we used information about the centroid, the minor and major axes lengths that form an ellipse, as well as the orientation of both of those axes. This information is used to create an ellipse around the masks to give us the information we need to find the largest length of the blood vessel and the aneurysm. Then we are able to extract from the metadata information about pixel dimensions in millimeters. And for us, it happened to be 0.3125 by 0.3125 by 0.6 millimeters. And then the major axis length is broken down into its components using Pythagorean theorem in order to convert pixel dimensions to millimeters. And finally, the largest diameter of the aneurysm and blood vessel is found, and then the size ratio is calculated.
For our verification and validation, we created 3 phantoms of known dimensions to test the accuracy of our program. The first phantom has a straight blood vessel and a spherical saccular aneurysm shown on the screen here on the left. The second phantom has a straight blood vessel with an ovular scapular aneurysm. And the third phantom has a splined curved blood vessel with a smaller spherical aneurysm.
The first test we used for verification and validation with these 3 phantoms resulted in first running through those 3 phantoms through the code, recording the measured max diameter of the blood vessel as well as the aneurysm, and comparing those values to the exact diameter of the blood vessel and aneurysm that we had formulated the 3 phantoms with those dimensions. We compared the exact values to the measured values to see if they were within our ideal and marginal values, so the plus or minus 1.2 millimeters. Of those 6 comparison, 5 of them passed yes, so they were within the plus or minus 1.2 millimeters. And the 6th one, the third phantom with comparing the max diameter of the aneurysm, failed, so it was above 1.2 millimeters, so it's 1.22 millimeters. So this overall experiment was a fail, but in the next few slides, Anna will also talk about why this, even though this experiment was a fail, why our project was still successful. The next experiment that we performed with these 3 phantoms was comparing the size ratio. So again, we ran through these 3 phantoms. We recorded the measured size ratio that was output through the code and compared it to the exact size ratio. We found the percent error between the measured and the exact values, which were shown here, between 6 and 34%. Our ideal and marginal value was just to have this percent error to be as minimal as possible, so this experiment was a pass. The last experiment that we used the phantoms for was for looking at the percent error of the percent change. So we used the phantom 1, first ran it through our code and recorded that measured max diameter of the aneurysm. We then used Phantom 1B, which was a phantom we also created that had an aneurysm that was 50% increased compared to Phantom 1. We ran that one as well through the code and got the measured max diameter of the aneurysm. We knew that comparing those actual max diameter of the aneurysms between the two phantoms were an actual percent change value of that 50%. We then compared the two measured max diameter of the aneurysms for Phantom 1 and Phantom 1B to find that measured percent change value, which was 51.4%. We compared that to the actual percent change of 50% to find the percent error between those two, and we got about 2.9%. This experiment was also the same, where we wanted our percent error to be minimized, so this was also a pass as well.
So to output our metrics and images, we created this user interface. It outputs the three metrics, which are the maximum diameter of the blood vessel, the maximum diameter of the aneurysm, and then the size ratio between the two. We also display two images. On the left, you can see the brain slice, which is used just to see the relative location of the aneurysm in the brain. And on the right, there's the aneurysm and vessel image, which is a zoomed up image of the aneurysm and vessel, the aneurysm in neon green, and the vessel surrounded by a dull green color. We also have this load images button in the left bottom hand corner, and that is for the user to start the algorithm and load in their two nifty files. So to make sure our interface satisfied the target specs, we tested it starting with the runtime. We ran 5 different image sets through the program, and we got an average runtime of 20.14 seconds on a 2016 laptop with an Intel i7 processor. This was well within our ideal and marginal values for the target spec, which was 5 to 10 minutes. We also verified that all the metrics and images appeared during each run.
Along with the verification tests that were just explained, there were many other tests done to verify our program was working properly. We tested everything from user instruction simplicity to having minimal error in the calculated size ratio. All of these tests, besides the minimal error of diameter measurements, passed. As Ali said before, the diameter measured of our splined aneurysm was off by 2/100ths of a millimeter, which likely would lead to no change in a clinical decision. However, one metric that is of great importance to note is the only 2.9% error that occurs when measuring the percent change between two aneurysms. This is important for monitoring the change of the size of an intracranial aneurysm over time, which is often what guides many clinical decisions.
So since our prototype is not going to be produced and our team had no budget for the year, we decided to look at cost analysis from a theoretical perspective and estimate the cost based on if this project were being developed at a company. The only cost to this project would have been the labor and the MATLAB subscription. So we ended up estimating our cost based on the work hours we actually put into the project and with a wage of $50 an hour. So the totals for the project come to 560 hours and $28,000. Also, since there are no current competitors on the market, and since the prototype would need many more iterations of work, we deemed it would be quite impossible to come up with an estimated selling price for the product.
Through our verification, we created multiple phantoms to run through our code to test the accuracy of our program. Along with allowing us to determine the accuracy of our project, these phantoms could be used as a verification tool for other research projects. Overall, we fulfilled the clinical need by creating a novel program that quickly obtains size metrics of an intracranial aneurysm that are useful to physicians and outputs those metrics to a user interface for easy viewing. The program also gives consistent results over time that will allow physicians to ultimately determine the best treatment plan for patients. Because of this, we deemed our project a success. We met customer needs while fulfilling a clinical need with a novel solution.
So if a team were to take over this project, we had a few ideas for future implementations. First, we talked about doing this phase 2 dual image processing. So right now we have one image set that is shown on our UI and those metrics associated with it. This phase 2 would have 2 image sets shown on the UI as well as their metrics for easy viewing for percent change in the aneurysm. Our next addition and future implementation for the project would be a few metrics. So the first would be the perpendicular height. Through our research, we found that this value, which is the measurement from the middle of the blood vessel, directly 90 degrees upward to the edge of the aneurysm, is important when the radiologist is analyzing the aneurysm. Due to lack of time, we were unable to get this measurement done. But in order to get this measurement for future teams, we would recommend using like a 3D representation in MATLAB to find the correct orientation first, and then finding the metric through that. Our last metric that we recommend looking into would be the skewness as well, which is the angle of the aneurysm from the vessel. This could also be measured through using a 3D representation through MATLAB, finding that same correct orientation and finding the angle from the blood vessel that the aneurysm is.
And finally, we would like to thank a couple of people who without their help, this project would not have been able to be complete. So first, Dr. Goldberg, thank you for bearing with us during a global pandemic. You have been an amazing professor, even since day one, who has wanted us to succeed, and we appreciate you for taking your time and being able to meet us and give us advice about all things senior design. And Dr. Adi, we extend our most sincere gratitude for you for your help throughout this entire process. This is a kind of a unique project to all of us, and we worked through a lot of things together, and we're grateful for your time and efforts. You are the definition of an amazing mentor, so thank you. And finally, Dr. Koch, we want to thank you for giving us a chance to work on this project and explore this unique idea. We appreciate your time and guidance, and it's been an amazing experience for all of us. And lastly, thank you to all of our viewers. We know you had lots of options for activities during today's quarantine, and we thank you for choosing us. Are there any questions?
Any questions? I have a quick question. So just on your first slide, you had a bunch of acronyms that I've never heard of, different methods for detecting aneurysms. So just to educate me, so I'm smarter about this topic, can you just explain what they are?
Sure. So are you talking about with MRA and CTA, IADSA?
Yeah.
Okay, so MRA is magnetic resonance angiography, and so it's using an MR technology to find blood vessels.
Okay.
And so CTA is where same sort of modality, and that's computed tomography angiography. And IADSA, that is for contrast, and it's not, it's more difficult to do from what I found, and it stands for intra-arterial digital subtraction angiography.
Okay, thanks. Actually, another question I have here is, you said one of your requirements was, in terms of like error, you needed to be within 1.2 millimeters of the actual diameter. So where did that number come from? Was that something, was there a particular standard, or was that something that was just kind of decided up front? Where did that come from?
So we decided on minus 1.2 millimeters because the dimensions, like the resolution of our images, each voxel had a specific dimension, and the largest dimension of that was 0.6 millimeters. And so we gave us forgiveness of 1 pixel on each side of the aneurysm. So that's where that 1.2 comes from.
Okay, so that represents like an error of 1 pixel width.
One on each
Correct.
side, yeah.
One on each side. Okay,
Yep.
okay, great, all right. And then I guess my last question would be, well, I have two, but okay. My second to last question would be, your report, you have, okay, it's like on here, line 8, it says 6.3 to 34% pass. Normally someone would look at that and say 34% error, you normally don't associate with being a pass. So can you just explain your kind of rationale behind that?
Yeah, I can explain that too. So we chose on that minimal as an ideal value for our error, simply because this is a novel solution. There's nothing like this that's been approved by the FDA or that is currently being used by physicians to diagnose or treat patients. And also in the research that we ourselves looked at, we were not able to find a percent error or a percent change from that specific size ratio metric that would lead to a change in treatment of a patient. So that's why we stayed on that minimal. It wouldn't. This metric alone is not affecting the ultimate decision.
I see. Okay. Then this is my last question. It kind of ties into that. Was your original goal for the project, was it basically to develop a proof of concept prototype, or was it to develop something that you could turn over to Dr. Koch tomorrow and he could start using it in the clinic?
So the entire purpose of this project was kind of to explore all of the ways that we could apply engineering techniques to this unique problem. So ultimately, it would not be used in a clinic as of tomorrow. It would be used kind of as a research tool to see all of the different ways that people could explore how to analyze intracranial aneurysms in people that have them. So I hope.
So it's more of a research tool then?
Yes.
I see. Okay. Do you foresee it someday being used as a diagnostic tool? Like somebody comes in with a severe headache and they do create an image and then they use your software to calculate something. Would they use that data to decide how to treat the patient? Do you see that happening someday?
Yes, I'm not entirely sure the date in which that could be implemented, because there's a lot more research that needs to go into this. But I think that in the future, in terms of radiology, this tool would be able to initially analyze an MRI image and give kind of like the beginning workings of information to a radiologist who then could analyze best options for treatment. I think that it definitely could be in the far away future or maybe near future. So yeah.
Great. No, I think you've done a really nice job with this. So, okay, good. Great. So that's it for my questions. Other questions?
I think Dr.
Yes. I have a question. So how dependent is the error on the spatial resolution of the images? In other words, let's say if you have a higher resolution images, would that reduce the error in your measurements?
So that would, with a higher spatial resolution, there would be more of an increased accuracy. So since our spatial resolution is so limited in this, that could be why like our accuracy, for example, the 34% was so high. So yeah, definitely higher spatial resolution would increase the accuracy, which definitely like a future team could take over and try to work with the spatial resolution on that. Yeah.
Thanks.
So if we can dig in on the 34% still, we're having a lot of fun talking about that. What do you think was driving that? So it's a size ratio. So what factors were driving that error to go up? What do you think?
Yeah, so Phantom number 3 was kind of different than the other 3 in terms of that it had that splined blood vessel. It did also have just a smaller spherical saccular aneurysm. So because of the splined, we were maybe thinking something with that and the way that our code worked. There could be some changes with that with the 34%. Again, with this one, we had the highest amount of discrepancies between the other Phantoms as well with this, not just the size ratio. In terms of our project, when we did this, because of lack of time, we weren't able to actually dive deep into why Phantom 3 had more error than the other 2. So we can't specifically answer that, why it's so high, but that, again, would be a future implementation for another team to take over and maybe look at, different Phantoms as well. So more spline Phantoms, maybe just different type of aneurysm as well. Could also lead to discrepancies as well. So yeah, we just didn't have time to dive into Phantom 3 and why it was so different.
What if I gave you a hint that it was the way that you're calculating that ratio that's allowing an error to drive up, particularly the mathematical operation that happens when you calculate a ratio? Does that make sense then? If you have a lot of air on the bottom, what happens? You have small numbers and a lot of air on the bottom. You inflate your air.
Right. That.
Oh,
Yeah.
those ratios are particularly vulnerable
Yeah.
to those types of things. So that's one of the dangers actually of using a ratio, and it's very difficult to come up with good, robust metrics for how well, because as soon as you get that's so small numbers with a decent amount of air in your denominator, it starts to blow up on you.
Yeah.
So that I think that's probably
Right.
how you were running into that, because you had the same level of error probably on every measurement. It had something to do with the geometry and the way you were calculating things on that. Does that make sense?
Yeah.
Yes, and that's a great point to analyze for any future implementations of this. So that's a good thing to take note of.
Dr. Audi, your hand's up.
I don't think he ever took it down.
Yeah, this is my I think I agree with Dr. Polk. You know, definitely the ratio is an issue. Yeah. So it's going to amplify an error, especially if you have a large one on the bottom. So.
I mean, this is not a trivial thing to worry about, though. This is something that we've actually thought about, with the research, with the startup companies and our grants and things that are looking at this. It's a legitimate and difficult thing to manage. I could tell you that the way that we've gotten around it is actually not relying on these ratios. There's almost no good way to get yourself out of the woods if you're using a ratio like that. So we're actually using much more complicated geometrical parameters that frankly don't have a denominator like that can blow up. So it's kind of cool that you ran into that, because that is one of the issues and the challenges with this, and you stumbled upon it.
And actually, some people, at least for some of the research we do, sometimes look at the log of the ratio as a way to minimize this issue with the amplification of the error when you're dividing two different numbers with error. But the other thing also, that I think it is really what probably make this number pretty large is that you change two different things from phantom 1 to phantom 3. You change the instead of having a straight blood vessel, now you have a bented one, and then also you have also an aneurysm with a much smaller diameter compared to the spatial resolution. Both of those things actually, in a way, made this error look much larger than the other first one and second one. So, but yeah, as you said, this is. But what I like about the phantom part is now you have a tool, a really nice simulation tool that can be used to compare your approach with other existing approaches or future approaches. So I think now you have a more objective way of comparing existing methods for quantifying the size of an aneurysm, which I think is an important outcome of this project. So.
Thank you. We appreciate all of those instances of feedback. If we had more time to explore this issue, I would love to, dive more into that and see what things we could create. Unfortunately, the pandemic gave us a little bit of a curveball, as well as the other classes that we had to maintain, but those are all really good notes. So
along those lines, if you can, I don't know if you've already done this in your final report, but maybe address those issues, the source of this 34% error and what things you might recommend a future team to look into to try to reduce that, and per Dr. Audi's comment, yeah, I agree with what he was saying. Your phantoms are impressive, and those could become a standard way of testing different methods, So you have kind of the makings of a standard here, a standard method of testing. You use these phantoms and you provide dimensions, that kind of thing, and that could be something people could use in the future. So, any other questions from anybody? Okay, I think then we're done for today.